Hello, in this lecture we'll find out the area of a circle. In the drawing we have quadrilateral ABCD. Inside this quadrilateral we have this circle. In addition, we know that side AB of this quadrilateral is equals to 2 units in its length, side BC equals to 8 units, side CD equals to 8 units in its length. This is angle ABC that is equal to 90 degrees in its side, and this is angle DCB that is also a right angle. It is equals to 90 degrees in its size. Again, our mission is to find out the area of this circle. So first of all, we will do a construction. That is to say, we will extend side DA and side CB of this quadrilateral ABCD until the two extended sides will touch each other. This is their touching point. We define the touching point of the extended two sides, side DA and side CB, as M. We define this angle as theta, and we'll focus on the right big triangle MCD. In this right big triangle MCD, this is the right angle. It is equals to 90 degrees in its size. This angle equals to theta according to our definition. Therefore, the missing angle must be equal to 90 degrees minus theta in its size. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Side CB, it is a side of a quadrilateral, therefore it is absolutely a straight line. When we extended the straight line CB by a straight line, the result is CM. And when we extend a straight line by a straight line, the result must be a straight line, so CM is a straight line. We'll focus on the upper side of the straight line CM at point B. Here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle ABM. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. So therefore the missing angle here must be equal to 90 degrees in its size in order to complete the sum of the angles in this right triangle ABM to 180 degrees. The missing angle here must be equal to 90 degrees. So we'll focus on this small right triangle ABM. In those right triangle ABM, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle must be equal to 90 degrees minus theta. So I'll write it down. In the next step, we'll prove that the right big triangle MDC is similar to the right small triangle MBA. So I'll write it down. And again, we'll prove that the right big triangle DCM is similar to the right small triangle MBA. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this is angle DCM in the big right triangle DCM. And it is equal to this angle in the small right triangle MBA, that is actually angle ABM. Repeat again. Angle DCM in the big right triangle DCM equals to angle ABM in the small right triangle MBA. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle theta, as it belongs to the big right triangle DCM, it will be defined as angle CMD. And if we relate to angle theta as it belongs to the small right triangle MBA, it will be defined as angle BMA. Repeat again. This equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is actually angle MDC in the big right triangle, and it is equal to this angle. That is actually angle MAB in the small triangle MBA. And repeat again. Angle MDC equals to angle MAB. Angle MDC in the big right triangle DCM equals to angle MAB in the small right triangle MBA. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually prove that all the three angles of the big right triangle DCM are correspondingly equal to all the three angles of the right small triangle MBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. The right big triangle DCM is similar. This is the sign of similar to the right small triangle MBA. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side DC of the big right triangle DCM over side AB of the small right triangle MBA equals to side CM of the big right triangle DCM over side BM or the right small triangle MBA. Repeat again. We derive that DC over AB equals to CM over BM. Side DC equals to 8 units in its length. Here side DC equals to 8 units in its length according to what is given as the question. We substitute DC by 8. Side AB equals to 2 units in its length according to what is given as the question. So DC over AB is 8 over 2, that is equals to CM. What is the length of CM? From the domain, it is very easy to see that CM equals to CB plus BM. That is to say, CM equals to CB, that is 8 plus BM. So in total, CM equals to 8 plus BM. So we substitute CM by 8 plus BM, and we have to divide it by BM. In conclusion, we found out that 8 over 2 equals to 8 plus BM over BM. 8 over 2 is 4, so 4 equals to 8 plus BM over BM. Here, we'll multiply this equation by 4, and we get that 4 times BM equals to 8 plus BM. Here we'll subtract BM from this equation, and we'll get that 4 BM minus BM is 3 BM equals to 8. Here we'll divide this equation by 3, and finally we will get that BM equals to 8 over 3 units in its length. So actually, this line segment BM equals to 8 over 3 units in its length, so I'll write it down in the drawing itself that BM equals to 8 over 3 units in its length. In the next step, we'll implement the Pythagoras theorem on the right small triangle, triangle MBA. By PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sums of the squares of the perpendiculars. The hypotenuse in the right triangle MBA is MA, so the square of the hypotenuse is MA squared, and it must be equal to AB squared plus BM squared. Repeat again. According to Pythagoras theorem in the right triangle MBM, MA squared equals to AB squared plus BM squared. So MA squared, that is the square of the hypotenuse, equals to AB squared. AB is 2. Here AB is 2. According to what is given as the question, so AB squared is 2 squared, that is 4, plus BM squared. We just right now found out that BM equals to 8 over 3, therefore BM squared is 8 over 3 squared. 8 over 3 squared equals to 8 squared, that is 64, over 3 squared, that is 9. So in total, MB squared equals to 64 over 9. So in conclusion, found out that MA squared equals to 4 plus 64 over 9. Here we will multiply 4 by 9 and then we will divide it by 9 in order to overcome the factor of 64 over 9. And we will get that MA squared equals to 4 times 9 is 36 plus 64 over 9. 36 plus 64 is 100 divided by 9. In conclusion, found out that MA squared equals to 100 over 9. Here we take a root out of this equation. And finally, we get that MA equals to the square root of 100 over 9. And the square root of 100 is 10. And the square root over 100 over 9. So the square root of 9 is 3. So in conclusion, found out that MA equals to 8 over 3 units in its length. So the hypotenuse MA equals to 8 over 3 units in its length. When I write it down in the original drawing, the hypotenuse MA equals to 8 over 3 units in its length. In the next step, we will do another construction. That is to say, we will draw perpendicular on side BC of quadrilateral ABCD in such a way that the perpendicular on BC will be also tangent to this circle. Again, we'll do construction in such a way that the perpendicular on BC will be also tangent to this circle. It's absolutely possible because you can draw the perpendicular on BC in any points on BC. Therefore, we choose the point on BC in such a way that the perpendicular on BC will be also tangent to this circle. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the perpendicular, the touching point of the perpendicular on BC and BC itself as point T. We define the point of tendency of the perpendicular with the circle, this point is point Z. We will extend the perpendicular TZ until it touches side AD of the quadrilateral. And we will define the touching point of the extended perpendicular TZ with side AD as point S. We will focus on the right triangle MST. In this right triangle MST, on the right triangle MST, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle here must be equal to 90 degrees minus theta. Okay. In the next step, we will define the center of this circle, this point as point O. We will define the point of tendency of tangent BT with this circle as point E. We will define the point of tendency of tangent AB with this circle as G. we join points O and E together by a straight line. Point O is the center of the circle, point E is the point of the circle itself. Therefore, OE is the radius of this circle. We define the radius of this circle as x. Therefore, OE equals to x. It is the radius of the circle. We can implement here rule number 1. I will remind you quickly what is rule number 1. Rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle and we have tangent AB that is tangent to this circle at point M. Point M is the point of tendency, and we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. We actually can implement one in our drawing. Why? Because in our drawing we have the radius OE that is drawn to point E. That is to say, it is drawn to point E, that is the point of tendency of tangent BT with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BT will be perpendicular to the radius EO. If BT is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. This is according to rule 1. In the next step, we join points O and Z together by a straight line. OZ is the radius of this circle. This is equal to x, according to our definition. Again, we have the radius OZ that is drawn to point Z, that is the point of tendency of tangent ST with this circle. Therefore, according to rule number 1, this angle equals to 90 degrees. This angle also equals to 90 degrees. Likewise, we join points O and G together by a straight line. OG is the radius of this circle that is equal to x according to our definition. Again, the radius OG is drawn to point G, and therefore according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So here, this is quadrilateral OZET. This small quadrilateral OZET, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 degrees times 3 is 270 degrees. Plus the fourth angle, the missing fourth angle. In total, the sum of these 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles in this quadrilateral OZET to 360 degrees, the missing angle here must be equal to 90 degrees. So inside quadrilateral OZET, we have 4 right angles. Therefore, we can relate to this quadrilateral as a rectangle. It is at least a rectangle, if not a square. So we relate to this quadrilateral as a rectangle, and we have the rule that the opposite sides of a rectangle are equal to each other. That is to say, side OZ equals to side ET. OZ equals to ET, but OZ is x, therefore ET must be also equal to x. Likewise, according to the same rule, side OE of rectangle OZET must be equal to the opposite side ZT. But OE equals to x, therefore ZT must be also equal to x units in its length. So we actually found out that quadrilateral OZET is not a rectangle but a square. Why? Because all of its sides are equal to each other if each side equals to x. Okay, we repeat on the same process on this quadrilateral, the small quadrilateral GOEB. In this quadrilateral GOEB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the fourth angle. In total, they must be equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees. So we relate to quadrilateral. This quadrilateral OGBE that has four right angles is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, side GO must be equal to the opposite side BE in rectangle GOBE. But GO equals to x, therefore BE must be also equal to x. Likewise, side OE must be equal to side TB in this rectangle TOBE. But OE equals to x, therefore TB must be also equal to x units in its length. So finally we actually found out that quadrilateral OTBE is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this quadrilateral is equal to x. In conclusion, we found out that line segment BT equals to x plus x, that is 2x. So I write it down. Line segment BT equals to 2x units in its length. In the next step, we will prove that the right big triangle SMT, this right big triangle, is similar to the right small triangle, triangle AMB. So I write it down. The right triangle STM, right big triangle STM, is similar to the right small triangle, triangle ABM. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this is angle STM, in the big right triangle, STM. And it is equal to this angle, that is actually angle MBA. In the small right triangle MBA. Repeat again. Angle STM in the right big triangle STM equals to angle MBA in the small right triangle MBA. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is a common angle that belongs to both triangles. So we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to angle theta as it belongs to the right triangle STM, we'll define it as angle SMT. And it is equal to itself. So if we relate to angle theta as it belongs to the small right triangle MBA, it will be defined as angle AMB. Repeat again. This equation means that angle theta equals to itself as a common side that belongs to both triangles. Okay. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually this is angle MST in the big right triangle. And it is equal to this angle, this is actually angle MAB in the small right triangle MBA. Repeat again. Angle MST in the big right triangle STM equals to angle MAB in the small right triangle MBA. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually proved that all the three angles of the right big triangle STM are correspondingly equal to all the three angles in the small right triangles MBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. The right big triangle STM is similar to the right small triangle MBA according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ST in the big right triangle STM over side AB in the small right triangle MBA equals to side TM in the big right triangle STM over side BM of the small right triangle MBA. Repeat again. We will derive that ST over AB equals to TM over BM, and it is also equals to side SM in the big right triangle STM over side AM in the small right triangle MBA. In conclusion, found out that ST over AB equals to TM over BM equals to SM over AM. ST is the missing side, so we leave it as it is, over AB. AB equals to 2, therefore we substitute AB by 2. And it is also equals to TM. What is TM? TM in total equals to TB plus BM. That is to say, TM equals to TB, that is x plus x, that is 2x, plus BM, that is 8 over 3. So in total, TM equals to 2x plus 8 over 3. So we'll substitute here TM by 2x plus 8 over 3, all divided by BM. BM equals to 8 over 3, so we substitute BM by 8 over 3. And it is also equals to SM over AM. SM what is the length of SM? From the drawing it is very easy to see that SM equals to SA plus AM. That is to say, SM equals to SA, that is this inside, plus AM, that is 10 over 3. So in total, SM equals to SA plus 10 over 3. So write it down, SM equals to SA plus 10 over 3 over AM. AM equals to 10 over 3, so we substitute AM here by 10 over 3. So those two sides, they are equal to each other. So we create the equation, the first equation from those two sides, they are equal to each other. That is to say, according to the first equation, ST over 2 equals to 2x plus 8 over 3 over 8 over 3. This is the first equation. So ST over 2 equals to, here we will multiply 2x by 3 and then we will divide it by 3 in order to have a common factor with 8 over 3. So 2x times 3 is 6x plus 8 over 3 divided by 8 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled and we left only with ST over 2 equals to 6x plus 8 over 8. So here we multiply this equation by 2. And we will get that ST equals to 6x plus 8 and 2 over 8 is 4. So 6x plus 8 over 4. In conclusion, we found out that ST equals to 6x plus 8 over 4. So ST equals to 6x over 4 is 1.5x plus 8 over 4. 8 over 4 is 2. So in conclusion, we found out that ST equals to 1.5x plus 2. So, can I know in the original drawing that the length of this line segment ST is 2 plus 1.5x. So I write it down. ST equals to 2 plus 1.5x in its length. Okay. We return to our equation, to the long equation. Those two sides are equal to each other. Therefore, we create equation equation 2 from those two sides that are equal to each other. So here we have this 2x plus 8 over 3 over 8 over 3. That is equals to SA plus 8 over 3 over 8 over 3. So really, this is the second equation that we created from the long equation. So So here we will multiply 2x by 3 and then we will divide it by 3 in order to work common factor with 8 over 3, and we get that 2x times 3 is 6x plus 8 over 3 over 8 over 3 that's equal to this expression. Here we'll multiply SA by 3 and then we'll divide it by 3 in order to have a common factor with 10 over 3. SA times 3 is 3SA plus 10 all divided by 3 divided by 10 over 3. So here in this side of the equation we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. Here also in the other side of the equation we have 3 in the numerator and 3 in the denominator, so 3 also will get cancelled. After we cancel 3 on both sides of the equation, we left only with, in this side of the equation we have 6x plus 8 over 8. That equals to 3SA plus 10 over 10. Repeat again. Actually found out that according to the second equation that we created, 6x plus 8 over 8 equals to 3SA plus 10 over 10. Here we cross multiply this equation and we get that 10 times 6x plus 8 equals to 8 times 3SA plus 10. Here we divide this equation by 2 and we get that 10 over 2 is 5, so it is 5 times 6x plus 8. That equals to 8 over 2 is 4, so it is 4 times, inside the brackets we have 3 SA plus 10. Here we will open the brackets on both sides of this equation and we get that 5 times 6x is 30x plus 5 times 8 is 40. That equals to 5 times 3SA is 12SA plus 4 times 10 is 40. So here we have 40 on both sides of the equation, so 40 will get cancelled and we left only with 30x, that is equals to 12SA. Here we divide this equation by 12 and finally we get that SA equals to 30x over 12, that is actually 2.5x. So we actually found out that line segment SA, this is line segment SA, that is equals to 2.5x in its length. So I write it down here in the drawing. SA equals to 2.5x. In the next step, I will copy the small quadrilateral ABTS or quadrilateral ASTB in a new page and with the circle inside it, and we will analyze this quadrilateral that actually blocks this circle. Of this circle is described by quadrilateral ASBT. So actually, this is quadrilateral ASBT that I copied from the original drawing. We define the point of tendency of tangent AB. We have a circle that is inscribed by this quadrilateral ABST. We define the point of tendency of tangent AB with this circle as H. We define the point of tendency of tangent BT with this circle as G. We define the point of tendency of tangent ST with this circle as K. And finally, we define the point of tendency of tangent AS with this circle as T. Actually, in this drawing, we can implement rule 2. I'll remind you what is rule 2. According to rule 2, the lengths of two tangents from common standpoint to the circle are equal. So we have here a circle and we have the common standpoint point P. From the common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, the lengths of those two tangents must be equal to each other. That is to say, PA equals to PB. We can actually implement rule 2 in our drawing. Why? Because if we focus on the common standpoint point A, from the common standpoint point A, we have two tangents to this circle, tangent AT and tangent AH. And according to rule 2, they are equal to each other. Repeat again. According to rule 2, if we focus on the common standpoint point A, tangent AT equals to tangent AH. So if we define one of those two tangents as A, then the other tangent must be equal to A because they are equal to each other. Again, if we define the length of tangent AT as A, then the length of tangent AH must be also equal to A because they are equal to each other. In the next step, we will focus on the common standpoint point B. From the common standpoint point B, we have two tangents to this circle. Tangent BH and tangent BG. And according to rule 2, they are equal to each other. That is to say, tangent BH equals to tangent BD according to rule 2. So if we define one of those two tangents as B, then the other tangent must be also equal to B because they are equal to each other. And again, if we define the length of this tangent BH as B, then the length of the other tangent BG must be equal also to B because they are equal to each other. In the next step, we will focus on the common standpoint point T. From the common standpoint point T, we have two tangents to this circle, tangent TG and tangent TK. according to rule 2, they are equal to each other. Again, Tg equals to Tk according to rule 2. So if we define the length of this tangent Tg is C, then the length of the other tangent Tk must be also equal to C because they are equal to each other. And finally, we focus on the common exam point, point S. For the common exam point, point S, we have two tangents to this circle, ST and SK. And according to rule 2, they are equal to each other. That is to say, ST equals to SA according to rule 2. So if we define actually ST equals to SK again, tangent ST equals to tangent SK here, and tangent ST equals to tangent SK. So if we define the length of tangent SK as D, then the length of tangent ST must be also equal to D because they are equal to each other. Okay. In the next step, we will add side AB to the opposite side, side ST. Again, AB plus ST. What is the value of AB plus ST? AB plus ST. From the drawing, it's very easy to see that AB in total equals to A plus B plus ST. ST in total equals to C plus D. So in conclusion, we found out that in quadrilateral ASBT, side AS, side AB plus the opposite side ST will be equal in total to A plus B plus C plus D. In the next step, we will add side AS to side BT. Again, we will add side AS to side BT in this quadrilateral ASBT. It is very easy to see from the drawing that AS plus BT equals in total to A plus B plus C plus D. Repeat again. We found out that AS plus BT also equals to A plus B plus C plus D. Exactly as AS plus AB plus ST. So those two expressions, they are both equal to A plus B plus C plus D, therefore they are equal to each other. So from those two equations, we derive that AB plus ST equals to AS plus BT. Okay. AB equals to 2, so we substitute AB by 2 plus ST. We already found out that ST equals to 2 plus 1.5x, so we substitute ST by 2 plus 1.5x. Here ST equals to 2 plus 1.5x and AB equals to 2. So it is equals to AS. AS equals to 2.5x. So substitute AS here by 2.5x plus BT. We have only found out that BT equals to x plus x, that is 2x. So BT equals to 2x. So substitute BT in this equation by 2x. In conclusion, we found out that 2 plus 1.5x equals to 2.5x plus 2x. 2 plus 2 is 4. So in this side of the equation, we have in total 4 plus 1.5x. That is equals to 2.5x plus 2x is 4.5x. So in conclusion, we found out that 4 plus 1.5x equals to 4.5x. Here we subtract 1.5x from this equation, and finally we get that 4 equals to 4.5x minus 1.5x is 3x. So in total we found out that 4 equals to 3x. Here we divide this equation by 3, and finally we get that x equals to 4 over 3 units. So actually found out that the radius x of this circle equals to 4 over 3 units in its length. Our mission is to find out the area of this circle. And we know that the area of any circle is equals to pi times the radius squared. If the radius is r, it is pi r squared. In our specific drawing, the radius of this circle is x, so it is pi times the radius squared. That's actually pi times x squared, because x is the radius. And we just right now found out that x equals to 4 over 3 units in its length, so it is pi times x is 4 over 3. So if x is 4 over 3, it means that x squared is 4 over 3 squared. So the area of the circle equals to pi times 4 over 3 squared. 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So actually found out that the area of the circle, the area that we are looking for, equals to either 16 pi over 9 square units, or in terms of numbers, it is equals to 5.585 square units. I'll repeat again. The area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equals to 5.585 square units. So in the next step, I will summarize the lecture. In this lecture, I found out the area of this circle. In the drawing, we have a quadrilateral ABCD. Inside this quadrilateral, we have this circle. We know that side AB of this quadrilateral equals to 2 units in length, side BC equals to 8 units, side DC equals to also to 8 units. This is angle ABC that is equals to 90 degrees in its size, and this angle DCB also equals to 90 degrees. Again, our mission is to find out the area of this circle. So, in the first step, we did a construction, that is to say, we extended side DA and side CB of this quadrilateral by a straight line until they touch each other. This is their touching point. We define their touching point as M. Then we define this angle as theta. We focus on the right big triangle, triangle DCM. The big right triangle DCM, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Then we focus, we know that BC is one side of this quadrilateral ABCD, therefore it is absolutely a straight line. And we extended the straight line BC by straight line. And we got line segment CM. When you extend the straight line by straight line, the result is a straight line, so CM is a straight line. CM is a straight line. If you focus on the upper side of the straight line CM at point B, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have in the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle that is angle ABM. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle here must be equal to 90 degrees. Okay? So angle ABM equals to 90 degrees, therefore triangle ABM is the right triangle. So in the right triangle, we focus on the right triangle ABM. This angle equals to 90 degrees, this angle equals to theta, therefore the missing angle must be equal to 90 degrees minus theta. Then we proved that the right big triangle DCM is similar to the right small triangle, triangle ABM. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common side that belongs to both triangles, so we can write down that angle theta equals to itself as a common side that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles of the right big triangle DCM are correspondingly equal to all the three angles of the right small triangle, triangle ABM. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side DC in the big triangle over side AB in the small triangle equals to side CM in the big triangle over side BM in the small triangle. I'm repeat again. DC over AB equals to CM over BM. DC is 8, AB is 2. CM, what is the length of CM? From the drawing, it is very easy to see that CM equals to CB plus BM. That is to say, CM equals to CB, that is 8, plus BM. So here, in total, CM equals to 8 plus BM. CM equals to 8 plus BM over BM. So if we found out that 8 over 2 equals to 8 plus BM over BM, 8 over 2 is 4, so 4 equals to 8 plus BM over BM. Here we multiply this equation by BM, and finally we found out that 4 times BM equals to 8 plus BM. Here we subtracted BM from this equation, and found out that 4BM minus BM is 3BM, so 3BM equals to 8. Here we divided this equation by 3 and finally found out that BM equals to 8 over 3 units in its length. Here. My segment BM equals to 8 over 3 units in its length. Then we focus on this right small triangle BM, and we implemented the Pythagoras theorem on this small right triangle BM. According to the Pythagoras theorem on this small right triangle BM, AM square equals to AB square plus BM square. Repeat again. In the right small triangle MBA, AM square equals to AB square plus BM square. So AM square or MA square, that is the square of the hypotenuse, equals to AB square. AB is 2, therefore B square is 2 squared, that is 4, plus BM square. We just right now found out that BM equals to 8 over 3, therefore BM square is 8 over 3 squared, that is 65 over 9. That is 64 over 9. And 8 over 3 squared equals to 64 over 9. So MA square equals to 4 plus 64 over 9. Here we multiplied 4 by 9 and then we divided by 9 in order to overcome a factor with 64 over 9. So MA square equals to 4 times 9 is 36. So in the numerator we have 36 plus 64 divided by 9. 36 plus 64 it is 100 divided by 9. So we found out that AM square equals to 100 over 9. We took a root out of this equation and finally found out that AM equals to the square root of 100 over 9. The square root of 100 is 10 and the square root of 9 is 3. So in conclusion we found out that MA, the hypotenuse MA equals to 10 over 3 units in its length. This is the hypotenuse AM that is equals to 10 over 3 units in its length. In the next step, we did another construction, that is to say, we drew perpendicular on side BC of quadrilateral ABCD in such a way that the perpendicular on BC will be also tangent to this circle. Okay? Again, the perpendicular that we drew on BC is also tangent to this circle at point Z. So we extended the perpendicular TZ until it touches side AD of the quadrilateral ABCD at point S. In this way we created the right triangle STM. In the right triangle STM, this angle equals to 90 degrees according to our construction. This angle equals to theta, therefore the missing angle must be equal to 90 degrees minus theta. Okay, then we define the center of this circle as O. We join points O and D together by a straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle that we defined as X. The radius OE is drawn to point E, that is the point of tendency of tangent or BT with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BT will be perpendicular to the radius EO. If BT is perpendicular to EO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Then we join points O and G together by a straight line. OG is the radius of this circle that is equal to X. The radius OG is drawn to point G. Therefore, according to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Likewise, we join points O and Z together by a straight line. OZ is the radius of this circle that is equal to X. The radius OZ is drawn to point Z. Therefore, according to rule 1, this angle equals to 90 degrees and this angle equals to 90 degrees. So in this quadrilateral OZET, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 degrees times 3 is 270 degrees, plus the size of the fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. Therefore, inside quadrilateral OZET, this quadrilateral we have 4 right angles, and therefore we can relate to this quadrilateral as a rectangle. It must be at least a rectangle, if not a square, so we relate to it as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle OZET, side OZ must be equal to side ET. But OZ equals to X, therefore ET must be also equal to X. Likewise, according to the same rule, OE must be equal to the opposite side ZT. But OE is X, therefore ZT must be also equal to X. So actually found out that quadrilateral OZET is not a rectangle but a square. Likewise, we repeated on the same process here. In quadrilateral TO in this quadrilateral GOBE, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. Therefore quadrilateral GOBE that has 4 right angles, we relate to it as a rectangle. And we know that the opposite sides of a rectangle are equal to each other, that is to say GO equals to BE. But GO is x, therefore BE must be also equal to x. Likewise, according to the sum rule, OE must be equal to GB. But OE is x, therefore GB must be also equal to x. So actually found out that quadrilateral GOBE, this quadrilateral, is not a rectangle but a square because all of its sides are equal to each other. Each side equals to x. In conclusion, we found out that line segment BT equals to in total to x plus x, that is 2x. So here line segment BT equals to 2x units in its length. Then we proved that the right big triangle STM is similar to the right small triangle MBA. Why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, it is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually prove that all the three angles of the right triangle, the right big triangle STM, are correspondingly equal to all the three angles of the right small triangle MBA. Therefore, those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that ST in the big triangle over AB in the small triangle equals to TM in the big triangle over BM in the small triangle, and it is also equals to SM in the big triangle over AM in the small triangle. I'll repeat again. We will derive that ST over AB equals to TM over BM equals to SM over AM. ST is the missing side, so we leave it as it is. AB is 2. What is the length of TM? TM equals to x plus x, that is 2x plus 8 over 3. Again, TM equals to 2x plus 8 over 3. Here. TM equals to 2x plus 8 over 3 over BM. BM equals to 8 over 3. Here. BM equals to 8 over 3, and it is also equals to SM. SM equals to SA plus 10 over 3. Again, SM equals to SA plus 10 over 3. And again, SM equals to SA plus 10 over 3. Over MA. MA is 10 over 3. Okay? So those two sides they are equal to each other, therefore we get the equation 1 from those two sides that are equal to each other. According to equation number 1, ST over 2 equals to 2x plus 8 over 3 plus 8 over 3. Here we multiply 2x by 3 and then we divide it by 3 in order to have a common factor with 8 over 3. And found out that ST over 2 equals to 2x times 3 is 6x. So in the numerator in total we have 6x plus 8 over 3 divided by 8 over 3. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. After we cancel 3, we left only in this side of the equation is ST over 2. That's equal to, on the other side of the equation, we left only 6x over 8 divided by 8. So ST over 2 equals to 6x plus 8 divided by 8. We multiply this equation by 2. And finally found out that ST equals to 6x plus 8 over 4. So ST equals to 6x over 4 is 1.5x, and plus 8 over 4. 8 over 4 is 2. So in conclusion, we found out that ST in total equals to 1.5x plus 2. If ST, this line segment ST equals to 2 plus 1.5x. Then those two sides they are equal to each other, therefore we created equation number 2 from those two sides that are equal to each other. So according to equation 2, according to equation 2, 6x plus 8 over 8 equals to, again, according to equation 2, according to equation 2, we found out that 2x plus 8 over 3 over 8 over 3 equals to SA plus 10 over 3 over 10 over 3. Here we multiply 2x by 3 and then we divide it by 3 in order to overcome a factor with 8 over 3. So 2x times 3 is 6x, so in the numerator we have in total 6x plus 8 over 3 divided by 8 over 3. In the other side of the equation we have SA plus 10 over 3 over 10 over 3. Here we multiplied SA by 3 and we divided it by 3 in order to overcome a factor with 10 over 3. So SA times 3 is 3SA, so in total in the numerator we have 3SA plus 10 over 3 divided by 10 over 3. In this side of the equation we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. In the other side of the equation we have here 3 in the numerator and 3 in the denominator, so 3 also will get cancelled. After we cancel 3 on both sides of the equation, we're left only with 6x. We're left only with, in this side of the equation, we have 6x plus 8 over 8. So, in this side of the equation we have 6x plus 8 over 8. In the other side of the equation we left with 3SA plus 10 over 10. 3SA plus 10 over 10. Here we cross multiplied this equation and found out that 10 times 6 plus 8 equals to 8 times 3SA plus 10. Here we divided this equation by 2 and found out that 10 over 2 is 5, so it is 5. Inside the brackets we have 6x plus 8, and 8 over 2 is 4, so inside the brackets we left with 3SA plus 10. Here we open the brackets on both sides of the equation and found out that 5 times 6x is 30x, plus 5 times s is 40, and it is equals to 4 times 3SA is 12SA, and 4 times 10 is 40. So here we have 40 on both sides of the equation, so 40 will get cancelled, and we left only with 30x, that equals to 12SA. Here we divided this equation by 12, and finally found out that SA equals to 30x over 12, that is 2.5x. So line segment SA equals to 2.5x in its length. This is line segment SA, it is equal to 2.5x in its length. Then I copied the quadrilateral ASTB in a new page. This quadrilateral ASTB blocks this circle, or this circle is described by quadrilateral ASTB. This is quadrilateral ASTB that I copied from the original drawing. In this quadrilateral ASTB, you can implement rule number 2. According to rule 2, if we focus on the common standpoint point A, we have two tangents to this circle, tangent AH and tangent AT. And according to rule 2, they are equal to each other. This is to say a t equals to ah. So if we define one side as a, then the other side must be also equal to a because they are equal to each other. Likewise, we focus on the common example point B. From the common example point B, we have two tangents to the second, tangent BH and tangent BG. And according to rule number 2, they are equal to each other. That is to say, BH equals to BG. BH equals to BG. So if we define one side as B, then the other side must be also equal to B because they are equal to each other. Likewise, we focus on the common example point T. From the common example point T, we have two tangents to this circle, tangent TK and tangent TG. And according to rule number 2, they are equal to each other. That is to say, TK equals to TG. TK equals to TG. So if we define one tangent as C, then the other tangent must be also equal to C because they are equal to each other, according to rule 2. And finally, we focus on the common standpoint point C. We focus on the common standpoint point S. From the common standpoint point S, we have two tangents to this circle, tangent ST and tangent SK. And according to rule 2, they are equal to each other. That is to say, ST equals to SK. And again, ST equals to SK according to rule 2. So if we define one side as D, then the other side must be also equal to D because they are equal to each other. Then we added side AB to side ST. What is the value of AB plus ST? From the drawing it is very easy to see that AB is A plus B and ST is C plus D. So in total AB plus ST equals to A plus B plus C plus D. It again, AB plus ST in total equals to A plus B plus C plus D. Then we added side AS to side BT. It is very easy to see from the drawing that AS plus BD in total it is equals to A plus B plus C plus D. Again, AS plus BT equals to A plus B plus C plus D. It again, AS plus BT also equals to A plus B plus C plus D. So those two expressions, they are both equal to A plus B plus C plus D, therefore they are equal to each other. That is to say, AB plus ST equals to AS plus BT. AB is 2, AB is 2. According to what is given in the question, AB is 2 plus ST. ST is 2 plus 1.5x. ST is 2 plus 1.5x and it is equals to AS. AS is 2.5x. Here AS is 2.5x plus BT. BT is x plus x, that is 2x. So BT is 2x. Here BT is 2x. So in conclusion, we found out that 2 plus 2 plus 1.5x equals to 0.5x plus 2x. 2 plus 2 is 4, so in total this side of the equation we have 4 plus 1.5x. That equals to 2.5x plus 2x is 4.5x. So in conclusion, we found out that 4 plus 1.5x equals to 4.5x. Here we subtracted 1.5x from this equation and finally found out that 4 equals to 4.5x minus 1.5x is 3x. So 4 equals to 3x. We divided this equation by 3 and finally found out that x equals to 4 over 3 units in its length. So the radius of this circle x equals to 4 over 3 units in its length. Our mission is to find out the area of this circle. The area of the circle, the area of any circle equals to pi times the radius of the circle squared. The radius of our circle is x according to our definition, therefore the area of our circle must be equal to pi times the radius squared, that is pi times x squared. X is 4 over 3, therefore pi x squared is pi times 4 over 3 squared. So the area of our circle equals to pi times 4 over 3 squared. 4 over 3 squared is 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, we found out that the area of our circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. Here again, the area of our circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equals to 5.585 square units. Okay, thank you very much.